Welcome to our Module 4 lecture on bias confounding and random error. The learning objectives for this module are to identify false conclusion mechanisms, so what causes false conclusions, figure out and how we can control or apply methods to control the risk of false conclusions, and then finally develop some skills that allow you to detect for bias and confounding in clinical studies. Now let's first introduce a clinical conundrum here as we go through this lecture. So here are these Oz nugget clinical conundrum. Scenario: a patient approaches your pharmacy counter with an advertisement featuring Dr. Oz. The ad claims, in a recent comparative study, patients that took Oz nuggets had a 40% lower risk of heart attack than patients who did not take Oz nuggets. That's pretty sweet. Dr. Oz has included a 2x2 table in the advertisement. Wow. Presenting data that appears to support this claim with a relative risk calculation of 0.6. Remember, relative risk. So 0.6, think about what that means. Suggesting a 40% lower risk of heart attacks. That's right, in patients taking Oz nuggets. So, with all this in mind, and you can see the 2x2 table there and the relative risk calculations, before recommending Oz nuggets, you need to critically evaluate the study before you tell this patient to actually do this. What additional information would you need to make an informed decision? How might bias, confounding, or random error have influenced these results? So let's think about this as we go through this lecture. At the base of this all, we need to figure out, is this study valid? What kind of validity does this study have? So we need to go beyond just basic analysis. So if we're just looking at association measures like relative risk and odds ratios, they're just merely a starting point for the interpretation of a study. We need to go further looking at internal validity. So if they're internally valid, it means they must eliminate bias, confounding, or random error. Okay? So basically, an internally valid study addresses whether the observed effects are generally due to the intervention or exposure. Versus external validity means it determines whether the results can be applied to clinical practice at broad or at large. Okay? So we need to go beyond just odds ratios, interpretations, or risk, relative risk, or whatever interpretation and statistic you're doing to look at internal and external validity to really understand and make recommendations to patients. So let's start with bias here. You, as the pharmacy student, are my Rocky Balboas, okay? Probably none of you know what that is, but that's an old movie with Sylvester Stallone, okay? And he was a boxer, and he came up from nothing, and he beat the champs, okay? He overcame insurmountable odds, and you must fight insurmountable bias odds in order to uncover the truth. So you are the Rocky Balboas. So we're going to use this as we go through the lecture. As silly as it sounds, just hang with it. And so your job is to figure out, where is bias in studies? And why is bias important? Because bias represents a systematic error in research that distorts the relationship between exposure and outcome. So it makes things wonky. It makes them not true. And if you don't know the truth of a relationship between variables, how are you going to make recommendations to real life people, to patients? These are real people who have real lives, who have real health, and you need to make recommendations that are going to affect their health and therefore their lives. That's why this is so important, and that's why you have to take it seriously. So bias is important because it impacts the results. It can affect both the magnitude and direction, as we will see, possibly making ineffective treatments effective or look effective, or make ineffectively looking treatments effective. It can go either way, and we'll see that, okay? And so as we go through this presentation, remember, you are Rocky, and you're going to fight bias. Good luck. Going a little more depth in bias, as we just heard, it's a systematic error, okay, that leads to an erroneous association between the exposure and the outcome. Those are the things we're always interested in, right? However, bias isn't generally the result of investigator prejudice or malice, but usually it's a foreseeable consequence of study design, and we'll see that, okay? Bias has both magnitude and direction, so it can make a relative risk of 2.4 appear as a relative risk of 2.1 or 2.7. That would be magnitude. It's changing the amount of the relative risk, and it can pull the association toward or away from the null value, meaning the direction. So magnitude and direction. And how do we prevent bias, or how do we remove bias? Prevention is key, right? We have to make study designs and do things before the studies even occurred to fix it. Because if you don't, it's hard to account for that after the fact. So as investigators who make studies, you have to account for where the bias is going to occur and implement strategies to minimize them. That's the only way to prevent or reduce bias, is to prevent it. So as understanding this is the first step to developing critical thinking skills that you as the student will need in this drug literature class. Bias generally comes in two different flavors. One being selection bias, which means that there are differences in the groups that we're trying to compare. All right, so that could be either those who participate in the study or those who don't, or between the groups in a randomized controlled trial, which leads to confounding. So this bias affects who enters the study and how they're grouped. Versus information bias is some sort of flaw or limitation in how you measure exposure or outcome data. Okay, and this bias affects the data collected during the study. So both impact study validity and require different detection and prevention approaches. Selection bias can occur, and often does, in observational studies, and so they occur because there's differences in how the study actually assigns them to the groups, or at least approaches them to be in the groups, affecting the outcome being measured. Okay, and we can see this in case control studies when the selection of a control is not representative of the population that produced the cases. And here's the example. With pap smear research, consider a study examining if pap smear prevents cervical cancer. So researchers enrolled 500 women with cervical cancer, those would be the cases, and asked them about recent pap smears. They selected controls by canvassing neighborhoods during the weekday hours. So then the observed data showed 40% of both cases and controlled had pap smear. So 1.0 would be the odds ratio, right? So suggesting no difference if you got a pap smear in protecting, or at least identifying, cervical cancer. However, the actual ratio is much lower, indicating strong protection from getting pap smears, because the bias occurred because the way they recruited the control group was women at home during weekdays who were less likely, for whatever reason, to have pap smears. So it's really critical and difficult to control for this bias in observational studies. You have to be very careful and very deliberate in how you obtain your groups in observational studies. Here are some more selection bias examples. So you can have exposure selection bias, meaning that this occurs in cohort studies when the comparisons in the groups differ in characteristics related to the outcome. Okay, you can also have attrition bias, meaning that those lost to follow-up differ between the group for whatever myriad of reasons or unknown reasons, and both can impact the results, right? They can both lead to incorrect conclusions about treatment effects, and so you need really careful selection of criteria and robust follow-up procedures to prevent these biases. So we can see a couple examples down here. One, in a smoking study comparing 10,000 cigarette smokers to 10,000 cigar smokers, revealed an apparently lower heart attack risk for cigarette smokers. However, this misleading result occurred because cigar smokers were predominantly middle-aged men, while more women smoked cigarettes. When examining only 5,000 men in each group, the heart attack incidence was identical, 1.0. So we can see what the selection bias was here due to underlying characteristics of those who smoke cigars versus those who smoke cigarettes. And then we can see attrition bias was demonstrated in a condom distribution study of HIV incidence in Africa, where 54% of the participants dropped out. That's a high dropout rate, making the dramatic results, 0.02 versus 0.32 incidence of HIV, difficult to interpret. High dropout rates can significantly undermine study validity because you don't know what happened to those people who left the study. Maybe all those people who left the study would actually make the incidence identical between the groups. We just don't know that. And then we have information biases, okay? And this can happen in both prospective and retrospective studies. And so they look like things of recall bias or reporting bias. When you give participants a survey, to recall past events, these are notoriously difficult to validate and usually are unreliable to a certain extent. So just think about an example of you were in a study and they asked you to tell them what you ate over the past week. You might think, I guess we could do that for a study, but try to actually think about what you personally ate each day over the past week. Pretty hard, huh? And then you could do previous records data. This is pretty good, although it has the chance for misclassification bias and assessment bias because historical data is used incorrectly or inconsistently between groups. And then finally, you can have information bias with investigator measurements because investigator bias can happen when they have knowledge of the study hypothesis, and so they unknowingly influence how they collect or interpret the data. In general, information bias affects the quality of data collected after the study begins. So that's why prevention is key here. Okay? And so it affects the accuracy, and so it makes just the data unreliable. It can distort the findings in otherwise well-designed studies. So prevention, again, is key. Going into a little more depth on the type of information biases. Recall bias, as we can see, I already mentioned, but we'll see an example here. In a study investigating whether children with spina bifida had mothers who experienced sore throats during pregnancy, mothers of affected children reported far more sore throats. This likely occurred because these mothers had more reason to deeply analyze their pregnancies compared to mothers with healthy children. So just think about being asked during pregnancy, so 9+ months, whether you had a sore throat. That's pretty hard. That's why recall bias is very difficult to deal with in studies, especially observational studies, which is where we see recall bias occurring. Reporting bias means when one group is more likely to report something versus another group, or one group is more likely to report it what they actually remember due to certain environmental factors like social desirability or other motivating factors, maybe embarrassment, something like that. So here's an example. Consider a study examining how many sexual partners men diagnosed with gonorrhea have had. Men in the gonorrhea group might report more partners, 3 versus 2, because they're required to notify partners for treatment. Meanwhile, men without gonorrhea might underreport partners due to social desirability concerns. Can you see there's actually reporting bias occurring in both groups in opposite directions? So it's really important when we evaluate studies to consider whether participants in different groups might have different motivations or abilities to recall or report accurately. A key bias to always consider. Now with the biases of assessment and misclassification, these are usually more technical in nature. And so something like inaccurate measurement is introduced by instruments. So for example, using abdominal x-rays to assess gastritis. When this image modality cannot detect the condition, would lead to erroneous conclusions about NSAIDs and gastric inflammation, right? Because even though you're using x-rays correctly, they're not being applied correctly to that outcome, or to that exposure and that outcome. Misclassification bias, so this is also called measurement error. And so this is what occurs when participants are incorrectly classified into an exposure or outcome group. So for example, in a study of blood thinners to prevent heart attacks, patients without heart attack might be incorrectly classified as having had them, skewing the results. So again, misclassification is in the word. You're putting patients in groups they shouldn't be in. So both these biases obviously can lead to underestimation or overestimation of true effects. Therefore, it's really important that we consider it when we're looking at studies, okay? Because we want to make sure whether the tools to measure the condition are appropriate and whether consistent criteria are applied to all participants regardless of the group assignment. These are the ways we reduce assessment and misclassification bias. Lastly, we have investigator bias, and so this is where an investigator introduces bias through their difference in how they solicit, record, or interpret information, okay, based on their knowledge of who's in what group. And so how do we prevent this? Blinding. That's why blinding is so sought after and considered part of the gold standard randomized controlled trial. It can substantially lower the risks as whether the investigator is doing it knowingly or unknowingly it ensures they aren't changing how they assess outcomes based on their knowledge of who's in what treatment group. So a real world example here, in a blood pressure medication randomized control trial, a physician who knows a patient is receiving active treatment might be confused by high blood pressure readings and request remeasurement, which often yields lower readings. Patients on placebo wouldn't receive the same attention. So an interesting application there of investigator bias that's not necessarily trying to influence the study, but just trying to understand why something's wrong. So actually identifying some sort of technical error, but still introduces biasy. Because if it's blinded, then that wouldn't happen in either group, and then probably the rate of that occurrence would be equal in the groups, therefore washing it out. Okay? So investigator bias is always something that can be subtle but powerful, but something we should always look at when we're assessing a study. So here's a summary of how you are going to be Rambo to assess all of this bias with all the biases we've talked about. So here's the table. This is a good table to know. It shows you how selection and information bias occur, the types, where it occurs, and the phases where we're worried about it. So how do you, as Rambo, apply and remember all these biases? Because it's kind of hard to keep it all tracked. And so then that leads to Rambo Man. So see, there's a point to this silly Rambo thing. Rambo Man will help you remember the bias types. So Rambo Man recruitment, how participants enter the study, there's potential bias there. Allocation, how participants are assigned to groups, what is the bias there? Maintenance, how participants are kept in their groups, what are the biases there? Blinding, who knows which treatment participants receive, what type of bias is there? And Man, so Rambo Man, objective measures and analysis for and how outcomes are measured and analyzed. So basically this helps you remember all the biases that will or could occur in research studies and help you to fight against them when you try to interpret this and apply this to real world patients. Let's dive into the Rambo Man framework a little bit more. As you can see, it has a natural flow from selection bias to information bias. Starting with recruitment, your question should always be, are recruited participants appropriate for the study's objectives? Because we're assessing selection bias. For allocation, are the groups allocated appropriately? Are they well matched? Again, selection bias. And finally, for selection bias, we're going to maintenance. Were the participants maintained in their groups? Were they compliant? Did they remain in the study? So here we're really assessing attrition bias, which is a subset of selection bias. Moving on to blinding, where the participants or investigators blinded, or both, were the statisticians, and this would help with investigator or information bias. Objective measures, where outcomes measured appropriately to assess information bias, assessment, misclassification bias. And finally, analysis, where analysis is appropriate, again, to help prevent information bias. This framework really helps you bring it all together, and I hope will help you remember all the biases that you need to assess a little more easily. So Rambo Man's great for systematic bias, but what about error that still occurs, which is always going to occur in studies to some extent, to some form, and it's called random error. No matter how well you design a study, there's always likely going to be some sort of random error occurring in it to some extent, but usually can be minimized. So when you evaluate random error, you want to ask questions like, is the sample size adequate? Because the larger sample size, is it powered adequately to reduce random error? Could the findings be due to chance alone? Are the statistical methods appropriate? How precise are the measurements? And are the confidence intervals narrow or wide? All these things tell you whether or not random error could be playing a role in your interpretation of the findings. Diving just a little more deeply into random error, again, it's that probability that the observed result is due to just chance, okay? An uncontrollable force that seems to have no assignable cause. And it's introduced because in research, we can only study outcomes based on samples and not on the entire world. So we can't know with confidence, 100% confidence, if something's always causal and rule out all random error. It's just not possible. So it can impact the results. It can influence magnitude and direction in both ways. But unlike bias, you can't really control for it. You can't really do much about it. It's always going to be there to some extent or some form. Two main sources are sample variability, so differences between the selected participants and the actual broader population of interest, and measurement error, meaning imprecision in the tools that we are using to measure our exposure and or outcome. So what are we talking about when I keep saying samples versus populations, right? So when we do a study, we can't study an entire population. We have to study a subset of the population of interest, okay? And then we make inferences from that sample to apply to the population at large. This is the only way we can do it. We don't have the capability to study the entire population because it would just be prohibitive. It would take forever. It would probably be highly inaccurate. So we're always taking samples. And so this sampling process necessarily introduces random error because there's no way to know with absolute certainty whether the total population would respond exactly the way as the sample. So hypothesis testing is what provides a framework for quantifying this uncertainty and making it a reasonable inference despite the random error that we know is always in a study. So what is this hypothesis framework that actually reduces or helps us to confidently say that random error is not causing the associations observed? Basically, we've learned about this in high school, right? You state a study hypothesis. So you articulate what the aims are. You typically have to say what the intervention has an effect on some groups in a meaningful way. You formulate the null hypothesis. So you basically create a hypothesis of no difference. So if a blood pressure medication you think affects blood pressure, the null hypothesis is that it does not affect blood pressure. And then you have to set the significance threshold, which is called alpha, which is what we'll be learning about too. And it represents the acceptable probability of falsely rejecting a true null hypothesis. So falsely rejecting, I know it's a double negative, so you're falsely rejecting it, saying that in your study you're saying, hey, there's an association, but actually there is no association because you falsely rejected the null hypothesis. The null hypothesis is true. So the alpha helps you prevent that error. You collect and analyze the data after you've done all these things, and then you obtain a p-value, which is related to the alpha value. And you make a statistical information. You compare that p-value to your alpha threshold, and then you can somewhat confidently reject or fail to reject the null hypothesis based on your stated hypotheses. And so this is the hypothesis testing framework. Let's make sure we understand null versus alternative hypotheses because it's kind of opposite of what you would think. So null hypothesis represents the hypothesis of no difference. So blood pressure medication does not affect blood pressure. Versus alternative hypothesis would be the hypothesis of difference. So in our Oz nugget example, we'll bring that finally back. The null hypothesis would be Oz nuggets do not decrease the incidence of heart attacks versus placebo, so a relative risk of 1. The alternative hypothesis would be Oz nuggets reduce the risk of heart attack compared to placebo, so a relative risk of less than 1. So hypothesis testing, remember, focuses on potentially rejecting the null rather than directly proving the alternative. It's based on the null. So, okay, if statistical evidence is not strong enough against the null hypothesis, we reject it, or if it is strong enough, we reject it in favor of the alternative. If it's not strong enough, we do not reject the null, and so there is no difference. Okay? So we can never definitively prove the alternative. That's the whole point of working off the null hypothesis. We'll never be able to prove the alternative causal relationship, but we can be pretty confident it exists based on certain statistical techniques and the way we set up our hypothesis. Now that we have an understanding of what the null hypothesis is, we have to establish certain values to test against in order to prevent certain error types. Okay, and so the value we always establish prior to testing a hypothesis is called the alpha value. And so this represents the acceptable probability of type 1 error. It's typically 0.05. That's what you're going to remember. P-values always look against 0.05, which is the alpha value. So if it's representing the acceptable probability of a type 1 error, that means there's a 5% chance of rejecting a null hypothesis when it's actually true, meaning a false positive. Okay? So you have a finding and you're like, hey, look, I have an association, but it's actually false. That's a false positive. That means you're willing to do a study where 5% of the time you do 100 studies, okay? And 5 of those studies, you're going to have a false positive. 95 of the times, you're going to have a true positive, okay? Statistical power, on the other hand, which usually is related to the beta value, okay, 1 minus beta, is typically around 80%. And it's the probability of correctly rejecting the false null hypothesis. So this helps to prevent the type 2 error, the failing to reject a null when it's actually false. So also called a false negative. So you did a study and you say, oh, I didn't find any difference, but it actually wasn't adequately powered. You have fallen into type 2 error, where you have failed to reject the null hypothesis when it's actually false. So that's probability is beta. So you need to understand these. You need to understand them well, alpha versus power and beta, type 1, type 2 error, where they overlap. Figure something out to know how you're going to remember them very well, okay? So how do we actually implement this in practice? This is from statistical significance testing, and we'll talk tons about this, okay? But you set your threshold, which is generally 0.05 for alpha in the medical literature. And then you perform your statistical tests to generate p-values, and you compare that p-value to the threshold, the alpha, that you predetermined. And if the p-value is less than the alpha, 0.05, you can say the results are statistically significant, and therefore you can reject the null hypothesis and be fairly sure that only 5% of the time you are falsely rejecting it. A false positive. Okay? What are these p-values? So p-values tell investigators the probability of obtaining the observed result, or a more extreme result, under the assumption that the null hypothesis is true. So they quantify the compatibility of the data with the null hypothesis. So a small value, typically less than that 0.05 alpha cutoff, suggests that the observed data would be unlikely if the null hypothesis were true. That's what it's testing. So here's an example. In a study comparing aspirin versus placebo for preventing heart attacks in elderly adults, finding a 4 versus 5% incidence, relative risk of 0.8, with a p-value of 0.6 means the difference could easily occur by chance. The high p-value suggests random error likely contributed to the observed difference. So the reason I'm just reading through the slide, because it's really critical. P-values are often misinterpreted. They do not tell us the probability that the null hypothesis is true, nor do they indicate the strength or importance of effect. They simply quantify the compatibility of our data with the null hypothesis of no effect, helping us to decide whether observed differences likely represent real-world effects or just random variation. So basically, it's telling us whether or not the random variation, which occurs in all data, remember regression to the mean, is occurring in your data, which explains any differences are seen, or if they're not due to chance and the differences are actually true. That's what a p-value is trying to get it at. Okay? So just remember, p-values are there to help us essentially figure out whether the data is due to chance or not, and not necessarily tell us the probability of the null hypothesis being true. Something that's helpful is looking at what an actual p-value is. And so what it does is it helps to characterize the distribution of possible test statistics under the null hypothesis. So you can see the bell curve on the left there. And that's all the area where your observed correlation could end up that you're looking at as characterized by a p-value. And so when it falls on one of the extremes, the little shaded portion there, it's usually something like less than 0.05. That means that there's only 5% likelihood, right? What we talked about in the previous slide regarding the null hypothesis. Okay? So when you have smaller and smaller p-values, you get less and less of a chance that your actual true value falls somewhere else on that giant bell curve that we're looking at, which is really the null value. There's no difference. So that's why a p-value is really characterizing a very small segment of that distribution and telling us that it's very likely that our observed p-value is truly significant and it's not a false positive. So to put it in another way, again, the p-value tells us about the probability of obtaining a given result, assuming that the null hypothesis is true. So it's the probability that you got the result in your study is 0.05 or less, so 5% or lower, assuming the null is true. Okay, so it helps us to rule out, again, random error creeping its way in there and then giving us a false positive. So when the p-value is less than alpha, less than 0.05 generally, this means that the observed difference is unlikely due to chance alone. Okay, but when it's above the alpha, or generally 0.05, indicates that there's insufficient evidence against the null hypothesis. So there's not proof that it's true. So remember, this is all the wording in statistics. It's important to note that failing to reject the null hypothesis is not the same as accepting it when the p-value is greater than alpha. We just simply acknowledge that our data set can't prove the null hypothesis is not correct. Okay? You could do another study and it could show it. So just kind of be careful with the wording there. Often in very well done studies, especially in JAMA and big journals, you're going to see confidence intervals. And confidence intervals kind of go alongside p-values, because p-values only tell us about statistical significance, but confidence intervals tell us both about significance and effect size. So let's start with an example. In our aspirin study, the relative risk was 0.8 with a 95% confidence interval. That 95% should ring a bell in your kind of mind because it matches up with the 0.05 or the 5% alpha rate, right? So the 95% confidence interval there was 0.4 to 1.2. So the confidence interval gives us the range of plausible values for the true effect, and it helps to consider sampling variability. Okay, so if you were to interpret this, you could do it in one of two ways. One would be a very strict statistical way. So if a study were repeated 100 times with 100-point estimates and 100 confidence intervals calculated, 95 out of 100 confidence intervals would contain the true measure of association. So if you look up online, you'll see these kind of traditional statistics books graphs where they plot a bunch of confidence intervals from different studies that fall in that range, 95 out of 100 times. A more practical definition would be the range of possible values within which the true magnitude effect lies with a stated level of certainty. So for aspirin example, we have a 95% confidence that the true risk reduction lies between 0.4 and 1.2. Okay, and that kind of makes sense because there's going to be that natural random variation around our estimate. So the confidence intervals give much more information than p-values alone, so that's why they're generally reported, at least required to be reported, especially in high-impact journals. Okay, and they tell us not just if it's significant, but also the precision of the estimate and the plausible range of true values. So it's really useful in trying to figure out clinical decision making. So in most epidemiological studies that they're looking at relative risk or odds ratio, right? These are calculations of our numerator and denominator, or a ratio, right? So when there's no difference, it's 1 because the numbers are the same. So when you see a confidence interval that doesn't cross 1 for relative risk or odds ratio, that means it would inherently and always have a p-value less than 0.05. That's just what happens because it doesn't cross 1, so it's statistically significant. However, if the confidence interval crosses 1, you know that the p-value would be greater than 0.05 because it crosses 1. So it would be not statistically significant. Okay, so you can see over on the right, there's an image showing all these repeated studies. And then you can see the one that goes up the middle. That would be no difference. And all the studies cross 1 at some point, meaning they're all statistically non-significant. So how wide a confidence interval tells us how certain we can be that the true result lies within that confidence interval. Okay? So the more narrow a confidence interval is, as you would expect, the more likely and the more confident we can be that the true estimate lies somewhere in there. And so this is where it's a little counterintuitive. A 99% confidence interval is going to have a much narrower width versus a 90% confidence interval has a much wider width. Why? Because you're only 90% confidence that you captured the true value. So your confidence interval is going to be much wider. You got to capture more values, so you're less confident. Versus 99% means it is inherently more strict. It has more precision, so it's a narrow interval. So you can be 99% confident you captured that true value. And this is really useful in terms of clinical utility, because even if you have a significant association with a 90% confidence interval, it might really throw it into question in terms of, well, 90% confident, if I'm treating a lot of patients over time, there's still a chance that this is actually making a difference, or they're at increased risk of side effects, or whatever the outcome is. So just something to think about with confidence interval width and precision. Now let's apply some of these concepts to the Oz nuggets example. So first we need to state the hypothesis. We believe that Oz nuggets will lower the incidence of heart attacks compared to placebo, therefore a relative risk of less than 1.0, which is the alternative hypothesis here, right? The null would be there is no difference, which is the next step. So we formulate the null, which would be a relative risk of 1.0. There's no difference between placebo and Oz nuggets. And then we need to set a significance threshold, which we generally always in medical literature set it to an alpha of 5% or 0.05. So there's only a 5% of a type 1 error, which again is falsely rejecting a true null hypothesis. Keep that one in your mind. Falsely rejecting a true null hypothesis. And so these are the first 3 steps to hypothesis testing with our example. After we've formulated our hypothesis and set the alpha value, we need to go ahead and continue with our Oz nugget example. So we collect the data, right? We look at the data and analyze it from a clinical trial, and then we apply statistical tests, which in this case would be a chi-square analysis, which you will learn more in a future module. And this is looking at the difference of heart attack incidence between the groups. This test yielded a p-value of 0.6, so what would that tell you? It indicates there's a 60% chance of attaining the observed result. Pretty low, right? And is it higher or lower than 0.05? So when we interpret the results, 0.6 is much higher than 0.05, although we don't really care about how much higher it is. It either is or isn't. It's a binary, yes or no. We failed to reject the null hypothesis. So remember, the null hypothesis here is that Oz nuggets and the placebo have no difference on heart attack rates. So despite the advertised 40% reduction, statistical analysis reveals the finding could easily be due to chance. So let's look at a few more examples here of statistical significance reporting methods that you could report either way, confidence intervals with a point estimate or p-value with a point estimate. So here's the example. Both of these have a relative risk of 2.0. On the left, we have a confidence interval of 1.5 to 2.5. So does that confidence interval cross 1? No, it doesn't, right? It does not include 1, so the result is statistically significant, despite the fact that we don't have a p-value there. So 2.0, the relative risk here, we can interpret as it's doubled in the exposure group. And we could be 95% confident that that true relative risk lies somewhere between 1.5, so not quite a doubling, to more of a doubling of risk. In contrast, someone could report the same relative risk in a paper on the right here with a p-value less than 0.01. So again, the relative risk is 2, so the probability of obtaining this result by chance is really less than 1% because the p-value is less than 0.01. So if the p-value is less than the predetermined alpha, which is 0.05, the result is considered statistically significant. We can still say that there's a doubling of risk, but we just don't know the true range where the estimate, or at least the confidence range where the estimate would lie. So we are a little more limited in that information, right? And so you can kind of see the differences here and why generally confidence intervals are more favored in the literature. Now let's say we've done our best to address all the biases, the Rambo man we talked about, and now we've tried to do statistical and power kind of pre-setups to reduce the chance of random error. But you can still have confounding, okay? And the way you have confounding is generally where baseline differences between the groups creep up, and it's not the fault of the investigator, it could be a bad setup, but generally it's not. It's just the chance of randomness creeping in, and then a third variable that's different between the groups actually drives differences in the exposure and the outcome, creating an apparent relationship that's not really there. So the way we try to detect this is really to look at the baseline characteristics between the study groups, and we have to see, are there any differences there that we need to account for, that's a limitation in the outcomes that we need to control for statistically. So for example, if patients taking Oz nuggets are significantly younger than those not taking them, and younger people obviously generally have a reduction in heart attack risk, right? Because you're younger, you have less time for those plaque to build up in your heart vessels. The apparent protective effect might be due to age rather than Oz nuggets. So that's an example of how a baseline demographic difference between the Oz nugget and the placebo group might drive what would seem like a reduction in heart attack for people treated with Oz nuggets, but it's really driven by age. This goes again over that third variable, the confounding variables. I generally call them confounding variables. Some people call them third variables that create kind of non-real associations between your intervention and your outcome. And the classic examples here is ice cream sales and murder rates both increase with heat, and coffee and cancer are linked through smoking. That seems like both bad things, right? But when you look at it, they're not really a causal relationship. It's only apparently a causal relationship because both ice cream sales and murder rates increase during hot weather. So there's something else that's driving that relationship. Similarly, coffee consumption was once associated with higher cancer rates, but this relationship was confounded by smoking because coffee drinkers were more likely to smoke. So that third variable that we didn't account for actually drove a false relationship there. So that's why it's really important when investigators conduct studies to do their best to really think before conducting the study on what do we need to measure in these patients, what's appropriate, what kind of variables need to be assessed, and sometimes assessing as many variables as can be possible and reasonable in a human subject study. Now, previously I said the way we detect, or at least get a hint of possible confounding in research, is to look at the baseline data. We look for statistically significant differences between groups and baseline data, and then we either control for it, or at least we know and we report that. That could be a confounding variable in the literature. So here's an example, the Oz nuggets that we kind of already mentioned. We're comparing Oz nuggets and placebo in the top row there based on age, blood pressure, baseline blood pressure, gender, and previous strokes. And so you can see here, the only two variables that are significantly different are age and blood pressure. And both of those variables are actually pretty important for heart attack risk. Okay, since both younger age and lower blood pressure, which is in the Oz nugget groups, independently reduce heart attack risk, these differences likely confound that reported relationship that Oz nuggets reduces heart attacks. So we would either need to put that in a limitation section, but even more likely we'd have to control for that in the statistical analyses, and it would most likely wash out the effect, I would imagine. But this is a good example of how a baseline group difference actually drives what I would call a non-real relationship between an intervention and an outcome. When we find these baseline differences, it's generally, as I keep saying, uncommon to report it as just a limitation, because you really need to see, is the statistical result you're reporting robust, meaning that it's not affected by the confounding variables. And so there's two strategies. You can either stratify or you can do multivariable regression. So stratification means you basically assess the study outcome separately within subgroups defined by the confounding variable. So for example, if gender or sex was a potential confounding variable, researchers could analyze outcomes separately for men and women to see if the treatment effect is consistent across genders. Similarly, with a multivariable regression, this one doesn't require you to break up the groups, but you actually use more complex statistical modeling where you can enter in that third variable, which could be sex or age, and see if the result remains statistically significant. And so multivariable regression is actually a very clever and cool way to do this, because you can add in more than one confounding variable. You could add in 6, 7, as many as you want. The more variables you add in, though, the less powerful the test becomes. So But both methods answer the question, what would the association between exposure and outcome look like if the groups were comparable on all confounding variables, which is really the question we want, okay? And so these are essential tools for addressing confounding in medical studies. In that example with Oz nuggets, we found that age is much lower, right, in the Oz nuggets group versus the placebo group. So let's figure out what happens when we stratify the groups based on age. So in a follow-up study with Oz nuggets, 200,000 patients, that's a huge one, the preliminary results showed an impressive relative risk of 0.25, suggesting Oz nuggets reduced heart attack by 75%. Wow. However, stratification by age revealed that this was entirely due to confounding. The age distribution was dramatically different between groups because most placebo patients were older. Nearly 75% were over age 65, while nearly 90% of the Oz nugget groups was below 65. So when you analyze it, right, the apparent relative risk was 0.25, but with the true relative risk, when we stratified by age, ended up being 1. Okay? So this is a good example of showing you that a third confounding variable, a variable that's not equal between groups at baseline, can actually drive a relationship that is not true between an intervention and an outcome. Here is what the stratification looks like in detail. So what you would do is you would redo the analysis between young and old patients because you want to really have them comparable, right? So you could break down older patients greater than 65, and you see all the numbers there in terms of how many young and old patients there were, or at least old patients in the Oz nugget and placebo group. On the right, you can see how many young patients were in the Oz nuggets and placebo group. And you can see when you rerun the relative risk calculation, they both become 1 in both groups. So you can see the original reporting of a relative risk of 0.25 was completely washed out in the stratification method here of redoing the relative risk calculation based on age of greater than 65 or less than 65. Now, doing a statistical kind of controlling or accounting for confounding variables isn't the only way, and really we actually want to prevent that. We don't want to do statistical adjustment because we want to be able to report a relative risk without any statistical adjustment, just because it lowers the power a little bit and it always makes it less certain. So what do? We have really good inclusion-exclusion criteria to make the groups as similar as possible, or if we're doing some sort of retrospective study or prospective cohort study, we would make sure the groups are matched really well. In a randomized control trial, we need to make sure that we have certain randomization processes in with large sample sizes in order to know that over time the demographics will likely be very balanced between the groups due to randomization's effect. And then finally, again, as we just talked about, you could statistically adjust for it if your other 3 kind of approaches to making sure that the groups are similar did not work so well. And here it goes more into detail on what you can do in each of those sections in terms of controlling for confounding. I'll just say here that when you're doing inclusion-exclusion criteria, you really need to do it carefully. You need to figure out, well, this is the population I'm studying, so what inclusion-exclusion criteria do we need to apply very carefully to make sure the groups come out similar on very key characteristics. In terms of group matching, what actual variables are we going to match on? Are we going to match on age and sex only? Are we going to match on previous heart attack rates? Things like that. Randomization, again, the larger you can randomize on, the better randomization works. There's also other kind of very statistically complicated ways to randomize rather than just roll the dice each time you have to assign someone treatment. And then, again, if the perfect balance isn't achieved, you can do something like stratification or multivariable regression analysis. And that brings us to the end of this module's lecture. And you can see we've gone over internal validity assessment. We're looking for bias, random man. And we've talked about random error and confounding and what you can do about it. We talked about statistical significance, alpha values, p-values, confidence intervals, and how you can adjust with confounding analysis. And you can see that all of these are going to come together in future modules to really help you understand how good a study is, and therefore how confident you can be to take those studies' findings and apply them to real human beings, to apply them to your grandma, to apply them to your brother and sister, to make decisions that are going to affect their lives. Because again, we might not be medical doctors, but we're still going to have a lot of responsibility in giving patients medications that always have risk profiles. There's no perfect medication out there. Everything has a trade-off. And so, although a medication can have a lot of benefits, it might have a lot of risks for a patient that they're not willing to tolerate. And so we have to be able to convey that to them in normal language from the literature that we know very well.